Good afternoon. Welcome everyone, and welcome to the second set of 2025 Simons Lections. So as many of you know, the Simons Lections is a distinguished series of lections that started 25 years ago. We typically have one speaker in pure mathematics and one in impure mathematics. And as one of my colleagues says, we have either one into inapplicable mathematics and the other one in impure mathematics. That's another option. And so this time we just had a few weeks ago Marina Wiazowska, and today I'm very excited to introduce Thomas Vidick. So Thomas has a very nice pedigree. He got his bachelor's from École Normale Supérieure, then did a master's at Paris 7, then a PhD at Berkeley, then a postdoc at MIT in CS, and then has been a professor at almost in a quantum state between Caltech, Weizmann Institute, and now École Polytechnique, Fédérale de Lausanne in EPFL. So his work is in quantum complexity, quantum cryptography, and related concepts. And for example, in his work, he has shown how entanglement, and I presume we'll hear about it in the next few lectures, how entanglement considerably improves the power of multi-proof or interactive proof systems. And in terms of complexity classes, that means MIP star is equal to RE, but we'll hopefully see some of this. So his research has received a number of prestigious awards, including he's a Simons investigator. He got the Michael Held Prize. He got the Blavatnik Award. And he got also the Pekaze from potentially defunct National Science Foundation. So please join me in welcoming Thomas.
So thanks a lot, Michel, for the introduction. Is the mic good? Yeah. So it's a great pleasure and an honor to be here and get a chance to tell you about a little bit about my research and what I get excited about. So just as a heads up, so the three lectures are going to be fairly introductory. So I see there's some experts in the audience, but I didn't prepare the lectures for you. I prepared it for people who haven't been exposed to this area before. And today I'm going to use slides, and tomorrow and the day after I'll say things that are a little bit more concrete on the board. So actually, Michel already went over this, but I realized when I was preparing the lecture a few days or a couple of weeks ago that this is a lecture in applied math, and I thought, oops, I never thought of myself as an applied mathematician. Applied math sounds a little bit like you have this nail and you're looking for a hammer, and mathematicians are there. They'll give you the hammer, and you'll nail the nail. But this is not usually how things are. Usually most of the work goes into finding the nail, and this identification of the nail is like a modeling step that goes, that is, interaction between the field that you're working on. It could be physics, could be biology, and mathematics. And the process of identifying this nail is what's interesting. And this is, can sometimes require math, but most often stimulates, motivates, generates some math just by itself. So that's the perspective I want to take for the talk. So I need to tell you a little bit what I'm going to talk about. So the theme that I chose is the theme of locality in computation. So what I mean by this is that computation is a process that takes inputs and transforms them into outputs. And this process is physical, so it obeys the laws of physics, which are generally local. So in order to study this theme, we're going to have to bring in a little bit of physics. And of course, we'll have to bring in some computer science, because computer science is the science of computation. And finally, it is my hope that in the process, by studying the objects that we'll study, we'll end up maybe stimulating, maybe generating, maybe answering some nice mathematics. So just to warm up, I want to start slowly with a couple historical figures. So first of all, David Hilbert, of course, is famous for his list of 23 unsolved problems at the ICM, and maybe his later work on the axiomatization of mathematics. But there's just two reasons I chose to put him first. One of the reasons is a funny quote, which I hear is like sort of a disputed quote, but I think it's representative of the pure mathematician's approach to applied mathematics. It's like, okay, we're going to solve. To his credit, so Hilbert was of course pure mathematician, but he did work a little bit in physics, and in particular axiomatization of field theories. So he worked with Einstein. And the second reason is the Hilbert space, which is going to be the mathematical foundation for my talk. So I assume it's not necessary in front of this audience to go through the definition of a Hilbert space, but in case, here it is. So now the name of Hilbert space wasn't given by Hilbert, it was given by von Neumann. Von Neumann is the second person I want to talk about. So von Neumann is more like closer to, let's say, my maybe ideal of the applied mathematician. So von Neumann is something that touched, like a huge range of fields from economics and game theory, automata theory, theory of computation. And each time, I'm not an expert, but it seems to me each time there was like a really interesting modeling task that he had to perform before, using math, or in many cases, developing math. So I want to focus on von Neumann's contributions to physics. So in the 1920s, there were two different approaches to quantum mechanics. There was Schrödinger's formalization of the theory based on differentiable functions and Schrödinger's equation. And there was Heisenberg's matrix mechanics based on finite dimensional matrices. And von Neumann realized that the two approaches could be unified by looking at by spaces of operators acting on infinite dimensional Hilbert spaces. And this is what he called von Neumann algebras. So we will get back to von Neumann algebras much later in the talk. The definition is not very important for us, but what's kind of relevant is that these algebras generalize simultaneously finite dimensional matrices, which have a non-commutative multiplication, and infinite dimensional functions that are infinite dimensional space. All right, so now I want to tell you a little bit about quantum mechanics. So quantum mechanics is the theory of individual particles. It's an amazingly successful and incredibly accurate theory. It has led to many technologies. These are MRIs, but also the laser and GPS through atomic clocks and all kinds of things. It's also a notoriously difficult theory, for one, because representing the state of a system that has n quantum degrees of freedom, like n photons, for example, this requires 2 to the n parameters. And that's even, when you're talking about finite dimensional things, but some branches of quantum mechanics, like quantum field theory, have to deal with, cancellations between infinitely large quantities. So it's a theory that's hard to work with at the computational level. And it's also a very delicate theory at the conceptual level. So you have to deal with, superpositions. What does that mean? The uncertainty principle, which limits how accurately you can make different kinds of observations, and entanglement, and the non-local properties of quantum mechanics. And in fact, it's the combination of these two, entanglement and the uncertainty principle, which led Einstein and Podolsky and Rosen to sort of question the completeness of the theory, thinking that it's not possible. There must be something that we don't understand about it. So this is a headline from the New York Times that I really like. But for quite a while, this was just the status of quantum theory, and these conceptual difficulties were mostly put aside. And it's the approach of shut up and calculate. So sure, there's these conceptual problems, not problems, but things that we don't necessarily understand. But it's fine as long as we're able to make good predictions. So it was like this for a few decades, and enter computer scientists and cryptographers. And it's in the late 1970s that for the first time people realized that, oh wait, so these things, uncertainty principle and non-locality, can be useful if we try to build things. For example, if you want to devise crypto systems, it's quite useful that some observations are incompatible, because it allows you to limit the amount of information that an adversary or an eavesdropper can gain about your quantum system, and that's the idea that underlies quantum key distribution, which is one of the real-life applications of quantum computing. So that's the 1980s. In the 1990s, there was very big development. People identified different equivalent models for quantum computation. So there's a notion of a quantum Turing machine, and there's a notion of a quantum circuit, and there's other ways, intuitively natural ways of defining computation based on quantum mechanics, and all of them turn out to be equivalent. And this gives a great strength to the theory, that there's different ways you can arrive at it, but you get the same notions. And this led to the discovery of quantum algorithms for problems such as, most famously, factoring, for which we didn't have classical algorithms. But the most important step in the development of quantum computing, I believe, came in the 2000s when, with the discovery of quantum error correction by Peter Shor. I don't know if Peter is here. Peter's here. Yeah, so Peter just showed up. Peter, perfect timing. So thanks to Peter, we learned that it's not like quantum mechanics is not like, you can also think about computation with nonlinear differential equations or computation with piles of sand or things like this. And all these models tend to be plagued by either the fact that they require infinite amount of energy, but you didn't realize, or that they're extremely sensitive to errors. And quantum computation is not, at least at the theoretical level, plagued by these kinds of errors. So it's a very robust model of computation. And what we're seeing now is like sort of experimental validation of the model. So for the first time, we have experiments that go at scales larger than what can be simulated classically, and for all we know at the moment, seem to work. All right, so this is going to be the physical theory that I choose to study my theme of locality in computation. We're going to work with quantum mechanics. And now I want to be a little bit more precise and model the kind of experiment that I want to study. So here is the foundation for the entire talk. So imagine that you have a universe, and this universe is going to be either classical or quantum. So in the classical case, the universe is completely specified by some variable omega that I imagine sampled from some probability space. This probability space could have a single omega in it, or it could be a bit larger. And this omega is a bunch of parameters that specifies my universe. And now I can make a certain number of observations on the universe. So I choose an observation, I label it using a variable u, and outcome for my observation. So this is a variable a sub u. And all the observations that I make will always have binary outcomes. So I make an observation, and the outcome I see is like either -1 or +1. And in classical mechanics, these outcomes can be computed from a description of the universe. So if I know what omega is, in principle, there's some function x sub u that I can compute on omega and will tell me what is the outcome of this observation. Okay, so that's if I make one observation. I can also decide to make a bunch of observations together, u, v, w, and in that case, I will observe some outcomes, au, av, aw, and each outcome is computed according to the corresponding function. And in this way, I can define probabilities of certain triples of outcomes being observed as a result of making triples, or could be larger numbers of observations. And the formula, I don't know, maybe is a little bit intimidating, but this is just an indicator function, right? I just took the expectation value of the indicator that xj is equal to aj. This is just because both xj and aj are ±1 valued, so this 1 plus thing by 2 is just 0 or 1, okay, depending if they're equal or not. All right. So that's for the classical setting. Now, in the quantum setting, I have a quantum universe. So the quantum universe is completely specified by quantum state, psi. So this is a unit vector in some Hilbert space, which could be finite dimensional, could be infinite dimensional. For the moment, think about a finite dimensional Hilbert space. And again, I can make different observations, and these observations will lead to outcomes. What changes is the rule that allows me to compute the outcome associated with a certain observation. Now we have to use the Born rule, which is the rule that governs probabilities in quantum mechanics. So instead of au being the value obtained by applying a certain function to the state of the universe, the distribution of au is governed by what we call an observable. So think of this observable as associating a value +1 or a value -1 to the outcome, depending on the state of the universe. But because quantum mechanics is linear, we can't just assign values plus minus 1 to all vectors in our Hilbert space in a completely arbitrary manner. We need to do that in a linear fashion. So this observable has certain eigenstates. The eigenstates of the observable are states that give definite outcomes. And in general, even knowing the state of the universe psi, the outcome that we obtain for the observation is going to be randomized and is going to have a certain expectation. And the law that governs the expectation is what I wrote here. So it's the overlap of the state of the universe on the observable. Okay? So throughout the talk, an observable is just going to be a square matrix that is self-adjoint and squares to the identity. What this just means is that it's diagonalizable with plus minus 1 eigenvalues. So it's kind of a non-commutative generalization of a plus minus 1 number, and it's the quantum mechanical generalization of the function x sub u that I had a little bit earlier. And so similar to before, we can, from the expectation, we can get the probability, and the probability that I get a certain outcome, given that I decided to make this observation, is given by the formula over there. Right now, continuing, we can also decide to make multiple observations, u, v, and w. In this case, we will get outcomes, AU, AV, and AW. And to each of these outcomes is going to be associated an observable, OU, OV, OW. What the observable is, it depends on the experimental setup and what quantity we're observing. I didn't write the probabilities here because it gets a little bit just annoying to write. But the expectation of the product of the outcomes will just be the overlap of the state on the product of the observables. And now here you see that I took a product of matrices, and the matrix product is not commutative. So the value that this expression can take depends in principle on the order in which I wrote the use. And we don't want that. So I'll posit for the rest of the talk that whenever in quantum mechanics I make 3 or 2 or 5 joint observations, I can only do that when the associated observables commute. And in that case, this expression doesn't depend on the product, and also it's always going to be a real number between minus 1 and 1. Okay. So this is how we access the universe. I'm going to make one further simplification, which I don't need to make, but it's a little bit nicer for later on. Instead of carrying this state psi all along, I'm going to imagine that the state of the universe is just given by the Hilbert space, and I choose a random state in that universe. And choosing a random state, this is equivalent to replacing the overlap with the state psi by a trace. So this is the trace, so it's just the sum of the diagonal entries, but it's also the expected overlap with a random state. And the trace should be normalized by the dimension. Okay, so what I really mean is 1 by dimension trace of the product of these 3 observables. Okay. So I have 2 models for the universe. I have a classical model, I have a quantum model, and in each model, I have a way to make different observations, and whenever I decide to observe different quantities, I have a certain rules that tells me what is the probability that distribution that I see on the outcomes of these observations. So now we're going to study these distributions. I'll refer to them as correlations, and I'm going to plot them so that you can visualize what's going on. So our setup is that we have a certain collection of observations that I can make. These are my u, v, w, so I imagine that I have a finite set of observations that I could make. And among these observations, some of them can be made jointly and some of them not. So I will fix a finite set of subsets of ut. T is a variable which governs how many observations I can make jointly. So let's say t is maybe 3 or 5. And I fix a set of subsets of size at most 5 of the universe, and these are, I refer to them as contexts, and they're all the sets of observations that can be made together. So these are like this is the data, this is my setup, and now I can represent every possible experiment using a distribution. So I drew a square here, and this square, each point in the square is a vector. It's a vector of probabilities. So for each set S in my collection of contexts curly set, so S is a set of observations that I can make jointly. If I make these observations S, I'm going to observe outcomes A sub S, so there will be as many outcomes as observations in the set. And so for each set that I can observe, I have a distribution over outcomes, and this gives me a vector of probabilities, and I plot it as a point here in my square. And now we can identify different subsets. First of all, there's one that I call the classical set. So the classical set is all such families of distributions that can be generated by a classical universe. So such that there is a classical universe that will generate these distributions. And I can similarly plot the quantum set, and these are all the families of distributions that can be generated in quantum mechanics. And on the picture, you can observe a few things. First of all, both of these sets are convex. Second, the classical set, I wrote it as a polytope, whereas the quantum set is a little bit curly. And thirdly, I drew the quantum set as being bigger than the classical set. So all these facts are easy to prove observations. Maybe the slightly, the one that requires a little bit of ingenuity is to show that the quantum set is bigger than the classical set. And so in order to make this whole discussion a little bit more concrete, I'm going to give you an example in the next slide. So the example is a famous example in quantum information. It's called the magic square. So this is an experiment where there's 9 possible observations that can be made. And just visually, I'm going to represent these 9 observations as the entries of a square. So I just label them 1, 2, 3, 4, 5, 6, 7, 8, 9. And you imagine that your universe is somewhere like behind this square, and you can decide to observe square number 2 or observe square number 5. And each time that you observe a square, you will get as outcome a plus minus 1 value. So all the squares can be observed individually, and furthermore, squares that are in the same row or the same column can also be observed jointly. Okay, so my collection of contexts here is all the rows and all the columns of the square. Okay. And now we'll ask a question. The question I ask is, does there exist a distribution, it's a classical or quantum universe that has the property that whenever you observe a row or a column, the product of the outcomes that you obtain are equal to always plus 1, except if you looked at the first row. If you look at the first row, I want the product of the outcomes to be minus 1. Okay, so here we will test a little bit if, or you can test for yourselves if you're following. So I can ask this question both of classical mechanics and of quantum mechanics. So in classical mechanics, the outcomes that I obtained are deterministic functions of the state of the universe. So I will fix the state of the universe, and then each of the squares, if I observe it, I will obtain a certain outcome plus minus 1. And so my question is it possible to associate plus minus 1 values to the entries of the square such that the product of the values in any row or column is plus 1 except the first row where it should be minus 1? Okay, and the answer to that is no. Thank you. Because if all the columns it's plus 1, then the product of all the entries by columns should be plus 1. But if you take the product of all the entries by rows, if in the first row you have minus 1 and then 1, 1, you would get minus 1. So it's a contradiction. Okay, so this distribution, in fact, any distribution that satisfies this condition does not exist in classical mechanics. So if I go back to my sets here, wherever is any point that satisfies this constraint has to lie outside of the classical set. What's interesting for us is that there exists a point in the quantum set that satisfies the constraints. So this point is just the following distribution. So for each row or column, the distribution on outcomes that you get is uniform over all the 4 possible triples that satisfy the constraint. Okay, so if you look at the first row, you will get a uniform triple such that the product is minus 1. And the column, you will get a uniform triple such that the product is plus 1. Okay? And this violates intuition because we just proved that it's not possible. The reason it is possible in quantum mechanics is that, oopsie, so sorry, I had written earlier, I removed it, is that there does exist 9 matrices. There are 4 by 4 matrices. They're square to identity and they're self-adjoint like I needed before. I could put these matrices in the squares in the 9 entries of my square, and whenever 3 matrices are in the same row or column, they will commute. And the product in any column will be the identity, and the product in any row will be identity or minus identity, depending on the row. But the 9 matrices together do not commute. So the proof we gave earlier that, if we take the product of everyone by columns or by rows, you should get the same answer, this doesn't apply when the entries of the square are matrices. The product of matrices can be identity or minus identity, depending on the order in which you take the product, and this is what's happening here. All right. So these are sets that are motivated by studying distributions in quantum mechanics. Now I want to bring in some element from computer science. So, and we will use complexity theory. So I want to talk a little bit about the complexity of asking different questions about these sets, similar to the question that we just asked about the, sort of the magic square. So note that the sets were convex. Convex sets are typically like sets that are kind of like easy, considered easy in optimization. And the classic questions that we can ask about convex sets are, there's two of them. First, there's the membership question. So given a vector of probabilities, is it in the classical set? Is it in the quantum set? That's one question I can ask. Another question I can ask is the optimization question. So given a linear function, so a linear function is just a collection of coefficients, what is the largest value that the linear function can take over either set, the classical set or the quantum set? So this is just a linear optimization problem over a convex set. And it's well known in the theory of convex optimization that, here I'm being like a tiny bit sloppy, but appropriately defined robust versions of these problems are equivalent. So for the talk, I'm going to focus on the linear optimization question, even though maybe the membership question is a little bit more natural. Okay, so I want to study the complexity of this problem. Given a linear function, what is the classical or quantum probability distribution that maximizes it? And in order to study it, I'm going to specialize a little bit the class of linear functions that we study. So if you remember where things come from, the set S, we think of it as a collection of inputs. They're observations that you can make. And A, they're outputs, they're outcomes that we observe. So we have these semantics in mind. If we have these semantics in mind, it's natural to look at linear functions that take the form of, well, firstly, we choose a distribution on observations that we make. So every element of curly S, so every set S is an observation I can make. I will take a distribution over observations that I can make. Then I get outcomes, and on the outcomes, I will place a constraint. So this is a distribution, and this phi S of A is just a 0, 1 valued function. So I think of it as a subset. There's a typo. It should be a subset of -1, 1 to the S. So the outcomes, they lie in the set -1, 1 to the S. And I will think of this linear function as specifying some outcomes that are valid, so they get a score of 1 according to the function, or they're invalid, so they get a score of 0 according to the function. So this formalization allows me to connect my linear optimization problem with a class of problems that's well studied in computer science and complexity theory, which is constraint satisfaction problems. Okay, so I'm now thinking of having a system of constraints, phi, so one constraint for each collection of observations. And these constraints are just constraints on the outcomes, okay? I want that if I make this observation, the parity of the outcomes should be 1. I want that if I make this observation, the AND of the outcomes should be 0, etc. So I can specify any such collection of constraints, a distribution on the observations that I make, and this will specify a linear function. And I can ask the question, what is the optimum of the linear function over this or that set? Okay, and these systems of constraints are called binary constraint systems, or I will call them binary constraint systems, abbreviated BCS. Binary just because I specialize to binary outcomes. All right, so that's the problem we want to study, and I will give a name to the two optimums. So if I given a linear function beta, the largest value it can take over the classical set is called omega subclassical, and the largest value it can take over the quantum set is called omega star. So for the example of the magic square game, I can design a beta, which is basically what I described before with a uniform distribution. And this way obtain a linear function whose optimum over the quantum set is bigger than the optimum over the classical set. And this is equivalent to the two sets being distinct. Okay, so I said that I would ask the question of how hard it is to compute these functions. So let me tell you a little bit what is known about this. So first of all, if we talk about the classical setup, so it's a very classic result in complexity theory, is Cook-Levin theorem, that given a system of local, so local here refers to the fact that the t, the size of the sets is, I think of it as a constant, 3, 4, 5. Given a local system of constraints, deciding this gives a linear function, and deciding whether the optimum of this linear function is 1 or less than 1. 1 here, you can think of it as arbitrary, but it comes from the normalization, the way I defined these linear functions. is a problem that's NP-complete. So NP-complete means that it's as hard as any problem whose solution can be verified in polynomial time. Now, kind of like very surprising result is that if you ask the same question in the quantum case for the quantum set, you obtain a problem that's undecidable. So undecidable is a very high level of complexity. It doesn't really matter what NP is for the talk, but what matters is that the quantum problem is much harder to decide than the classical problem. What makes this possible in a way is that for a classical universe, you always have an efficient way to check if there's a solution or not, because you're only looking about plus minus one variables. You can enumerate over those. In the quantum case, you have to enumerate over observables, these matrices, in some dimension, but I didn't specify what the dimension of the observables is. This is some kind of hidden parameter that is not bounded a priori. And so it's possible for this problem to be indecidable because of that. All right, so now this is sort of the exact decision problem. This might not be representative of the kind of like the real complexity of the problem, because in general you don't have infinite precision. In the classical case, this is not so relevant, but in the quantum case, you could be worried about precision issues. So now let's talk about the bounded error problem. So not deciding between the optimum being 1 and almost 1, just strictly less than 1, but being 1 and less than, let's say, half, where half is arbitrary. So it's another famous theorem in computer science, the PCP theorem, and we have some also people who worked on that in the audience here. That deciding whether the optimum of this linear function is 1 or strictly less than half has the same complexity as the problem without the half promise. And the theorem that we prove with Anand, who's in the audience, and other co-authors, is that in the quantum case, also the bounded error problem is just as hard as the exact decision problem. It remains undecidable. So I'll talk a little bit about consequences of this in a few minutes, but I don't have time to do like proofs or anything. I just want to say a few words about how these theorems are proved, and tomorrow on the board I will go a little bit more slowly about certain aspects of the proof. So firstly, the classical result. So it's proved. There's different ways to think about this, and I'm going to be a little bit rough, but think of it as being proved in 2 steps. So the starting point is a system of constraints, and these are local constraints, and these constraints are on a certain number of variables. There's 4 on the board, but in general there would be more variables. And what we know is that this system of constraints is either satisfiable or not satisfiable. And our goal is to transform it into a system of constraints that, if it was satisfiable, it remains satisfiable, and if it was not satisfiable, now it becomes far from satisfiable. So I'll do it in 2 steps. The first step is kind of easy, so you're going to amplify the case where the system is far from satisfiable by taking many combinations of constraints. I'm not saying exactly how this is done, but imagine that if you combine all these constraints together, instead of checking one constraint at random, you check a collection of constraints at random, then you will be more likely to detect a problem if the system is not satisfiable. But this has a downside. The downside is that I went from local constraints to constraints that now might require looking at all the variables at the same time, because I'm combining all the constraints together. And so the second step is going to step by which we're going to reduce the locality of the constraints. And this is the main step in the argument. It's going to lose a little bit in the gap here, but I don't worry about this here. I want to worry about this. And this is going to be done using error correcting codes. And I'll describe that tomorrow. So we will encode the variables into a longer collection of variables, such that 2 things can be done. First of all, whenever I had a constraint that now looks at all the variables to start with, on my encoding of the variables, this will be a constraint that's much simpler. It will only need to look at maybe 1 or maybe 2 entries of the longer assignment. And then I will have to add a few constraints. Firstly, to check that the encoding is a valid encoding, so that this x prime is a valid encoding of something. And I will also have constraints that check consistency with the original string that I copied over there. All right. So very roughly speaking, we have these 2 steps of amplification and locality reduction. in the classical setting. Now in the kind of like quantum or non-commutative setting, we want to mimic those. So the two steps actually go through almost unchanged, but there's some interesting difficulties. So let me just tell you about the difficulties. So I'm trying to do the same transformation with the same guarantees. So there's difficulties both for the completeness and the soundness, where the completeness is the first arrow and the soundness is the second arrow. So for the completeness, remember that in the quantum setting, we have this condition that whenever I want to impose a constraint, it's required that the associated observables should commute. So I need to make sure that if in the starting system, whenever there's a constraint, the associated observables commuted, in the ending system, this is also the case. So this creates all kinds of difficulties that can be resolved. The second difficulty, which is more interesting, is to analyze the soundness. And so this is just arguing that if there's a collection of observables that satisfy the new constraints, then this can be pulled back to a collection of observables that satisfy the original constraints. And we'll discuss that a little bit more slowly tomorrow. What I want to point out here is that in the quantum case, there's a third step that can be done. And this is basically the reason why we have one problem that can be undecidable when the other has bounded complexity. It's in NP, which is a bounded time class. And this is the fact that in the quantum case, we can do length reduction. So you can observe that the reductions that we made here, they had one effect, which is that I end up with a slightly longer universe, if you want, a slightly longer number of possible observations or variables that could be made. And this is because this encoding that we performed in order to allow us to check multiple constraints locally. Now, in the quantum case, there is going to be a procedure of length reduction where we take a long proof like this one here, and we simulate it by a shorter proof. And the way to simulate a shorter proof when the entries of the proof are observables is by considering direct sums or block decompositions. So here on the right-hand side, I have a block matrix whose two blocks are the two observables, OI and OJ, that are on the left-hand side. And I introduced a new variable, which is just a block matrix identity minus identity. And now you can see that if I look at the product of these two observables, I will obtain, when I make the first observable measurement, if I condition on obtaining a +1 eigenvalue, so a +1 outcome, the other observable will look at OI. And if I condition on obtaining a -1 outcome, the other observable will become OJ. So this is something, maybe I would say for people who study complexity theory. So in complexity, it's kind of like understood that you cannot, in general, reduce the length of a proof. And this is analogous to reducing the randomness that's used by the verification procedure in order to select an entry in the proof. And you cannot reduce randomness because you cannot like kind of delegate randomness to the proof. But in the quantum setting, we are able to delegate randomness, so the choice of this observable to the proof here. All right, so far what I did is I described my setup of universes and local observations classically and quantumly, and I gave you some results about the complexity of optimizing linear functions over these sets. Now I want to spend the time that we have left to loop back to mathematics and operator algebras and von Neumann algebras and try to say a few things there. All right, so I introduced a classical set and a quantum set earlier. The quantum set I defined using finite dimensional Hilbert spaces and finite dimensional operators. In general, in quantum mechanics, there is not really any reason to limit ourselves to finite dimensional Hilbert spaces. We can also consider infinite dimensional Hilbert spaces. And this motivates the introduction, at least in principle, of another set, C, the QC subscript. It stands for quantum commuting, such that points in that set are defined exactly as the points in the quantum set, except that I allow the observables to be infinite dimensional. So the mathematical framework for working with infinite dimensional bounded operators, this is the framework that was developed by von Neumann, the framework of von Neumann algebras. So it again doesn't really matter what's a von Neumann algebra, but think of here tau as an infinite dimensional, the trace, if you have an infinite matrix, is not going to converge. So you need an appropriate infinite dimensional generalization of this, and now I allow infinite dimensional matrices. And I can define, a new kind of universe, which is, you could say this is just playing, but actually in quantum field theory, you do have to work with infinite dimensional spaces in order to model the kind of things that you want to model. And this quantum computing set was introduced in the 1980s by mathematical physicist Lausanne, who was studying quantum correlations, and he asked the question, if you take the limit of finite dimensional correlations, are you able to reproduce the infinite dimensional ones? And this is a little bit of, like a side question maybe in the foundations of quantum mechanics, and just like earlier the problems with quantum mechanics, you can put it aside and simply work with the model that you want, and this is basically what was done until this question gained a little bit of prominence through a series of equivalences with other problems in math. So it started with a problem that was posed by Cons. So Cons was working on classification of von Neumann algebras depending on the kinds of traces that the von Neumann algebras have. And in his work of classification, he asked a question, which was not a crucial question, but he asked the question whether a certain kind of von Neumann algebra, so type 2-1 von Neumann algebras, these are infinite dimensional von Neumann algebras that are nicely behaved, whether these von Neumann algebras have some kind of finite approximations. Basically, whether this infinite dimensional algebra can be reasonably well approximated by algebras of finite dimensional matrices. And this again was asked kind of in passing and then put aside until the work of Kirchberg. So Kirchberg is someone who works in C-star algebra theory. And Kirchberg had his own conjecture about tensor products of C-star algebras that I'm not going to go over. But Kirchberg showed that Kahn's embedding problem and this conjecture are equivalent, and also to a whole lot of other conjectures. For example, there's conjectures in free entropy of Voiculescu and some conjectures in group theory that I will get to in a minute that are equivalent to these conjectures. So even though Tsirelson's problem and Kahn's embedding problem by themselves didn't attract so much attention, the fact that they were later connected to a whole lot of conjectures, all having to do with finite approximations of certain infinite objects, gave it a lot of prominence. And I find it quite remarkable that there's a whole family of conjectures in algebras that are equivalent to a very simple problem about whether two nicely defined convex sets are equal or not. So surely that one we should be able to resolve. And the second surprise is that we can resolve that question. Actually, I already told you almost everything that is required to resolve the question. All right, so we have two different convex sets, like the quantum one and the infinite dimensional quantum one. And to answer Tsirelson's problem, we'd like to show that they're equal or to show that they're different. So how do you show that two convex sets are, let's say, different? Well, it's enough to take a linear function and show that the maximum of this linear function on the one side is bigger than the other set. Right? It's what we did already with the quantum set and the classical set. But now we're talking about two quantum sets. It's a little bit harder. We're not going to manage to directly show that these two optimums are distinct, but we'll show it indirectly using a nice argument. So the argument is as follows. So I can look at the optimum that this function has in the quantum set and in the classical set. I'm trying to show that they're different. Instead of showing that they're different, I can try to ask, oh, okay, well, how do you compute them in the first place, like before? Okay, the optimum over the quantum set you can approach from below by kind of like enumeration. Okay, this is a supremum over all finite dimensional matrices, so you can take nets and you can increase the dimension, and you can have a sequence of values that eventually, you don't know how fast, but eventually is going to converge to this one. The other one is a little bit harder to see, but with some work, and you need the definitions to show that, it's possible to get a sequence of bounds that approaches from above. This is done by considering convex relaxations of this set that are a bit bigger but nicer to describe, so over which you can optimize. And so you get a sequence of, you get algorithms that approach the purple value from above. Now, if you remember what we did before, I showed you that the blue value, the optimum, is uncomputable. Okay, it's uncomputable even to determine if it's 1 or less than half. I mean, so even impossible to approximate. So now, if the blue and purple values were equal, you would get a contradiction because you'd have an algorithm that computes the blue value simply by performing both procedures from below and from above, and you run them, and because you know that both of them converge, if both of them converge to the same value, you will have a stopping criterion, which is once they're sufficiently close to each other, you stop. That will give you an algorithm. But we showed that there's no algorithm. So it means that the two value must be different. Okay? So this is like separating convex sets using complexity, a little bit surprising. But it ends up having some nice consequences in math. So now this might seem like a little bit specific, and just to finish, I want to tell you about some other approximation problems that you might hope to tackle using the same approach, and one of them which we successfully tackled using the same approach. So one famous problem in group theory is the sophicity conjecture of Gromov. So a countable but infinite group is sophic if informally this group has non-trivial approximate representations in finite dimensions. Okay, so here sigma is not a morphism; it's just a map from the group to permutation groups of dimension n. So for every n, you have such a map, and it's required that the map in the limit reproduces the multiplication law of the group. That's the first bullet, and separates non-trivial elements from the identity. Okay. So if instead of goes to 0, I said equals 0, this would just be sigma as a representation of the group. Now I'm asking for it to be an approximate representation of the group. So the motivation for studying this condition is that firstly, many groups are sophic. So it's obviously a generalization of the condition of a group being residually finite, and you can show that, for example, amenable groups and many other, also some non-amenable groups are sophic. On the one hand, and on the other hand, sophic groups tend to be very nice. For example, they satisfy what's known as Grotschall's surjectivity conjecture in ergodic theory. That's just an example, but they satisfy all kinds of conjectures that you wish would be true for every group, but you can only show it for the case of sophic group by essentially like proving it for finite groups and then managing to take limits in the appropriate way. And so conjecture that was posed by Gromov is whether, or question is whether every countable group is sophic. Okay, I'm not going to answer that question. So a slight relaxation of the question is the same question, but now you look for approximate representations, not in permutations, but in unitary matrices. So you have a little bit more freedom. You don't require that the things are permutation, just that they're unitaries. And so now, instead of the group being called sophic, is called hyperlinear. So every sophic group is hyperlinear, but the converse is not necessarily true. And you can ask the same question: are all countable groups hyperlinear? So far these are questions in group theory, but a very nice result of Slofstra is that the answer to this question is yes. So every group is hyperlinear if and only if for every LCS. So we studied binary constraint systems earlier. These are linear constraint systems. Okay, so the constraints that you put on the observables, they must be linear constraints. So only about the product of the observations that you see. So if and only if for these class of linear functions, then the quantum and the infinite dimensional quantum value would be equal. Okay, and so once you know that, and you've seen what I told you before, it gives you an approach to trying to show that there exists a non-hyperlinear group. Here's what you're going to do. First of all, I told you about this result earlier. That is that for not linear, okay, but just general binary constraint systems, the problem of computing or even approximating the quantum value is undecidable. And we only also know, I didn't say it, but if you restrict to linear systems of linear constraints, the problem of deciding whether the value is 1 or strictly less than 1 is undecidable. This is again a very surprising result because systems of linear constraints, classically you can solve using Gaussian elimination. So it's not even that it's in NP, it's in P. But the quantum version remains undecidable. And so you could hope that building on both of these results, you're able to show that also for linear constraint systems, the bounded approximation problem remains undecidable, and this would allow you to show that there is a non-hyperlinear group. So we don't know if this is possible so far, but we managed to do something a little bit weaker than that, which resolves another conjecture, which you can formulate as a conjecture in group theory, but I'll formulate it as a conjecture about in graph theory. So it's known as the Aldous-Lyons conjecture. So here's the setup for the conjecture. So you consider finite graphs, or actually finite or infinite graphs. Think of these graphs as having a bounded degree, and they have a designated distribution on the vertices that allows me to randomly pick a root of the graph. Okay, so I have two distributions. First, I have a distribution on graphs. And for each graph in the support of the distribution, I have a distribution on its vertices that allows me to select a root. Okay, so these are called random rooted graphs. The important part is not that the graph is random, is that the root is random. Then I can define a notion of distance on random rooted graphs as follows. I'm going to define neighborhoods. So you take a graph, you take a random root, and you look at neighborhoods of increasing sizes. Because the root was chosen at random, what you obtain is a distribution on neighborhoods of radius 1, 2, 3, etc. in the graph distance. And this allows you to compare graphs of different sizes. You can even compare an infinite size graph with a finite size graph simply by checking if they have small neighborhoods such that the distribution on neighborhoods that you get are close for the one graph and the other in total variation distance. And as long as you discount the importance of larger neighborhoods with their size, you can have finite graphs that are very close to infinite graphs. Not arbitrarily close, but very close. So this metric was on graphs was introduced by Aldous and Lyons, and they studied convergent sequences according to this metric. So you can take a sequence of finite graphs and have it be convergent, and ask, okay, what can I say about the limit? And they observed that the limit satisfied some nice regularity properties, and most important of which is the notion of being unimodular. So I'm not defining unimodular, but you can think of it as a kind of a condition about symmetric transport in the graph. So flows in one direction are equal to flows in the other direction. Something like this is a very natural condition. And for unimodular graphs, they were able to show a lot of theorems. They're able to analyze convergence of random walks on unimodular graphs and study all kinds of graph algorithms on them. And so they asked the question, or made the conjecture, it would be nice if every unimodular graph was a limit of finite ones. Sorry, not for unimodular graphs. So for limits of finite graphs, they're able to show the theorems, and they'd like to extend them to every unimodular graph, which you could do if every unimodular graph was a limit of finite graphs. But this one we were able to show that so this is Louis Bowen, Michael Chapman, and Alex Lubotsky, who was visiting, but I don't know if he talked about this. Even though this problem can look like a little bit different from what we studied so far, it has a little bit of the flavor in the sense that you have an infinite object, you have some finite objects, and the question is, when can the infinite object be approached by the finite dimensional ones? And so you can try to apply the same proof strategy. And so this is what we did. First of all, we defined a restricted class of constraint systems that have a name. The name doesn't matter. It's a bit more general than the linear constraint systems, but more restricted than general constraint systems. So this gives you a class of linear functions. And then you define two values, which is the optimum that your linear function takes when evaluated over the finite graphs, and the optimum that it takes when evaluated over the infinite unimodular graphs. And if you manage to show that there's a function in your class such that these two optimum are different, you're done. But maybe you don't know how to do that because you'd have to construct like complicated graphs. So instead you study the computability of the functions, and you show that the one can be approached from below by definition, the other by above by definition, and this is where all the work goes, that at least one of these two values is uncomputable. And so you deduce by the same argument that I gave you earlier that the two values are different, and so you've separated the two classes of graphs, and that refutes the conjecture. I'm gonna end very soon. I wanted to just do like a sidestep. So in this whole part of the talk, I considered kind of like a specific way of generalizing classical distributions and classical complexity to quantum. And the way we did is that classically you study constraint satisfaction problems. I replaced those by the same constraint satisfaction problems, but I associated a quantum value. The main thing that I did is I replaced classical plus minus one, this should be xu, classical plus minus one variables xu by quantum observables, which were these like kind of non-commutative variables of arbitrary dimension. And this is, you could think of this as being like the Heisenberg picture of doing this, if you see what I mean. So Heisenberg picture is talking about how you model the observations that you make, as opposed to how you model the underlying object. What primes is the description of the operator that allows you that models the observation. You can try to do the translation in the Schrödinger picture, and you obtain questions in quantum complexity that seem very different. So there you would replace classical variables by by quantum variables, because what primes is the variable. Quantum variable is like you replace a bit by a qubit, where a qubit now will be a unit vector in two-dimensional space. And the system of constraints now becomes what's called a local Hamiltonian. And I'll discuss this like day after tomorrow. And in that area, there's also some questions about complexity that are open and that seem to have a very different flavor from the previous, from what we discussed today, even though the starting point is the same theory that you're trying to generalize to the quantum case. So if you want to know, here is the plan. So tomorrow I want to go back to like the proof sketch that was like really fast, and I want to break it down into 3 different pieces and explain a little bit how this is done. And my goal tomorrow will be to arrive at some questions in stability. So some questions about stability of representations in group theory. This is kind of like the heart of the proof, but in order to motivate these questions, I'll first go over like a little bit the structure of the group, and then I'll state these questions and say a few things that are known about this. And on Wednesday is going to be completely different. I'll talk about the second generalization. So I'll talk about this this conjecture called the quantum PCP conjecture, and I won't, I'll just go very quickly over that, but my goal there is to talk about quantum error correcting codes and how these codes are themselves connected to nice problems in high dimensional, in topology and the study of chain complexes. So it'll be like very different kinds of math, but I hope I'll do it at a very elementary level, hoping there also to like bring up some nice questions. Yeah, that's it.
Any questions?
Thanks for a very nice talk. So about this approximation theory question, I guess many people doing computational physics want to simulate physics, right? And usually they use finite computers. So could you comment on, if do we expect that there will be phenomena in nature that are just fundamentally infinite, and we're just not able to approximate using finite computers?
I don't know. It's not doesn't seem absurd to me that so I don't have an experiment that I can describe that requires an infinite dimensional Hilbert space, and such that whatever you'd observe in that experiment cannot be reproduced. I mean, I have, but it requires you to solve the halting problem basically, which I don't really expect the universe to do. So that part I don't expect. But it's not, I mean, I don't know, it's not unreasonable to me that this wouldn't be the end of the story. That somehow by studying, let's say, quantum field theory, you'd end up having some phenomena that can actually be observed and that do not have some finite descriptions. I know this is anathema to computer scientists, that everything should be finite and finitely approximable. It seems reasonable to me, but it's not like, I mean, I don't know, physics is its own.
Michel in the introduction mentioned something about multiple provers and interaction, and I'd never heard about multiple provers in the talk. Did I not miss everything?
I skipped that because my experience of trying to talk about interactive proofs to mathematicians has been like, just doesn't work. So someone else can give maybe you would do it better. So but I guess you know the answer to your question. So in order to study the complexity of constraint satisfaction problems, and when I had this proof sketch where you manipulate the constraint satisfaction problem by introducing additional variables, considering encoding, combining constraints together, you can do that at a purely combinatorial level by talking about constraints, but it's very delicate, and not everything, we don't know how to do everything there directly. It ends up being very productive to broaden the model a little bit, and instead of study just like constraint satisfaction problems the way I define them, study a much broader class of verification procedures. Instead of imagining that you read a proof and you get, so this just like very naive model I had of interacting with the universe, like broadening that a little bit, allowing different kinds of interactions, And this gives us the setting of interactive proofs that's studied in complexity theory. And this is, this goes into the proof of some of the statements that I described. But I preferred to state them without interactive proofs because I'm hoping it's more approachable. But
So just to clarify, so the result that you described, which showed the undecidability
this
of
is
this
equivalent
problem,
to MIP star equals R, yeah.
that's
I just didn't want to go there to not add, but yeah.
Questions? So I have a questions for you. So when you show the two convex sets, I forgot the names of the convex sets, but so you showed essentially they were different because one was you could use SOS hierarchies to optimize over one of them, and then it was undecidable on the others. Do you have any? Is there any natural convex set in the middle where you could show that where you could potentially hope for being able to show points that belongs to one and not to the other that would be easily computable in between?
So no, I don't know a natural set in between, but what would you want of that set in between?
I mean to be easy. I mean, so I presume the problem with the SOS hierarchy is that you cannot easily show a point that belongs to CQC and that does not belong to C star.
Yeah, so we have such points, but right, they're not easy to, yeah. No, I don't have, no, so I don't have any, no. I mean, in a way, like, I don't know how that would happen because, I mean, if I was able to put a set in between that somehow is easier to describe or easier to work with, then I imagined I would already have separated the two of them, so, which,
I mean,
yeah.
maybe a conjectural set.
Right, so that would give like maybe like easier, no. We don't, this has been very studied in quantum information, just the fact that it's hard to work with the quantum model because you have these problems with dimensions that you don't know how to bound. So it's also a problem of like not only theoretical, like in my talk, but also practical interest to identify relaxations, all kinds of relaxations. And it's true that in general you want to be able to compute using the relaxation, and that's what motivates sum of squares. If you drop the fact that you want to be able to compute with it, but you just want something, yeah, I don't know.
Any final question?
Hi, thank you very much for the talk. A simple question, I'm maybe stupid, but would you explain what do you mean by uncomputability?
It's
something
in the
which is
Turing sense. So I mean, here, I mean, at a technical level, I mean exactly as hard as solving the halting problem. So what I mean is that there does not exist an algorithmic procedure that, given as input a specification of the problem, so the linear function, is going in finite time to stop with some, okay, and let's say I also give it some approximation parameter epsilon, is going in finite time to stop and return a number that is within epsilon. So these procedures, the problem that they have is that they do converge, so uncomputable doesn't mean that there isn't a procedure that eventually converges to the value. But I mean, this is fine. The problem here is that you don't know, you have no way of telling when you're close. And so you can run your procedure and it can say 3/4, 3/4, 3/4, 3/4. And you don't know if you shouldn't be going one more step that is going to stay, say, 7/8 or something. And then, yeah, so this is with the halting problem where you have a Turing machine and you're running and trying to decide if it's going to halt or not, and it hasn't halted so far. And you know that if it halts and you continue long enough, it will halt, but you don't know how long to.
And the issue is that here both the approximation from below and above must converge at some point, so you do know that it's going to stop.
If the two values were equal, because they converge to the same value, I would have a way to tell when I have an epsilon approximation. I know that at some point the two of them will be within epsilon of each other, and when that happens, I can stop. It doesn't matter that I don't know when it's going to happen. I know it's going to happen, so I have a stopping criterion. If you don't have that, you don't have a stopping criterion.
Perfect. Thank you very much.
This is a follow-up on Michelle's question. So we have these sets where deciding membership is not computable. So there's I guess, a subset of points which can be proven to be in C star. And there's a subset of CQC of points that can be proven to be in CQC.
Okay.
Is it known whether those subsets are equal to each other or are different from each other?
Yeah, sounds like a nice question. I'm not sure. So can that be formalized properly? So do you need to specify what is the algorithm that you're using to prove that they're in the one set or the other, or you can define that in like in logic or in a way that because like any given point can be proven just by giving a certificate for C star for the quantum set.
Right, right.
Because any point in that set does have like a collection of finite dimensional matrices that proves membership in the set. That's not the case for the other one. So I mean, you can definitely study subclasses. I don't know. Sounds like a nice question. I'm not sure how to formalize it properly, so I'd have to think about it a bit more.
Thanks.
So it depends what you mean explicit. I mean, there is. So I didn't say it, but you can, appealing to, like some recursion theorems about Turing machines, you can define an explicit set in the one set and not the other. So I can, we have like a piece of code that prints out, all the probabilities. So we didn't use it because we don't have enough paper, but it like. So you can define an explicit point in one of the other. I thought the question was about like maybe identifying some subsets that have like maybe better computability properties than others.
Yeah. So there's two layers in the results that you show. One is sort of using this reduction to undecidability to prove the difference between the closure of a set and some target set. And there's the quantum aspect of it. And I was wondering if you remove the quantum aspect of it, do you know of examples where undecidability has been used as a primitive to show that some finite approximation to some set did not exist, or you have to go to the complexity of undecidable quantum problems for that?
Maybe it's a question to the audience. If someone has an example, like I would be interested. I don't see why this would have anything to do. So where it helps us is that if you accept. It's not clear at all to me that to separate, maybe that's a question I could have stated, like just separate the two sets without appealing to complexity theory. So this, in principle, is possible, but we don't know how to do it. If you accept that you're going to appeal to complexity theory, then it really helps you to have an underlying model. It doesn't need to be quantum computing, but we have an underlying model of computation that allows us to do reductions, and it's a bit funny because even though this will come up tomorrow, even though in the end we're just talking about computability, so you could say this is not, it's almost like logic. Who needs complexity? To prove the result, we do need to appeal to notions of polynomial time and algorithms and things like this, and then it helps to have a model of computation. But yeah, no, I don't know.
Any final question?
Actually, sorry.
You have a question?
Many questions.
So let's thank Thomas again.